So let us solve this initial value problem. We'll begin by rewriting this given differential equation. So we'll keep the second term and take the first term to the right hand side. So that will be negative of x squared plus y squared dx, which can be also rewritten as dy over dx equals to negative times x squared plus y squared divided by xy, or simply dy over dx equals to negative x over y minus y over x. Now, this is a homogeneous differential equation. That is because if we consider the expression on the right hand side, and let's say we represent it by the function f, now we're going to make a substitution. We'll substitute x with lambda x and y with lambda y. And this is going to give back the original function fx comma y, which can be also written as fx comma y multiplied to a factor lambda raised to the power of 0. So that means we have a homogeneous function of degree 0. Now since this is a homogeneous function, so we have a homogeneous differential equation. Now how do we solve such a type of differential equation? All we have to do is we have to let y equals to v times x. And we'll differentiate both sides with respect to x. So that will give us dy over dx equals to, so here we have to apply the product rule. So that will be v plus x times dv over dx. So let's substitute this into our differential equation. So we will get v plus x times dv over dx equals to minus, so here we have x over y, so that will become negative 1 over v minus y over x, so that will become v. So further solving this, we have x dv over dx equals to negative 1 over v minus 2v. And if we combine these two terms, then we will get, now what we can do, we can separate the differential. So we have v divided by 1 plus 2v squared dv, and this is equals to negative dx over x. So this is in the variable separable form. Now we can integrate both sides. To integrate the integral on the left hand side, we will do is we will multiply with 4 and divide by 4 and rewrite this integral as. So the integration on the left hand side is extremely simple to solve. All we have to do is make a simple substitution. 1 plus 2v squared equals to some variable, let's say t, and that is going to give us natural log of 1 plus 2v squared equals to, so we have negative 4 times, so dx over x, the integral will be natural log of x. Now we also have to have a constant of integration since everything is in terms of logarithm. So we will consider natural log of c. Right. So we have natural log of 1 plus 2v squared equals to log of x raised to the power of negative 4. Here we have used the property being a times log of b. So that simply equals to log of b raised to the power of a plus log of c. Now what we'll do, we'll combine these two logarithm. Now we have logarithm on both sides, so we can get rid of the logarithm to have the absolute value 1 plus 2v squared equals to c raised divided by x raised to the power of 4. Now this value is always positive, so this will be simply 1 plus 2v squared. We can get rid of the absolute value. Then we have absolute value of c divided by x raised to the power of 4, because x raised to the power of 4 is also going to be a positive value. Next, we replace the value of v with y over x. So we have 1 plus 2 times y squared over x squared equals to absolute value of c divided by x raised to the power of 4. Let's multiply throughout with x raised to the power of 4. So we have x raised to the power of 4 plus 2 times x squared y squared equals to absolute value of c. Now, we will use the initial condition y of 1 equals to 1 to obtain the value of c. This simply means that when our value x approaches 1, then y is going to approach the value 1 as well. So let's substitute this. So we will have 1 raised to the power of 4, so that's going to be 1 plus 2 times 1 squared plus 1 squared, so that's 2 equals to c. So our c value is 3, which is a positive number. We can simply see that c is equals to 3. So therefore, our final solution is given by x raised to the power of 4 plus 2 times x squared y squared. So this is equals to 3. So this is the required solution to our given differential equation.